Here's a terrifying thought. The best evidence yet for life beyond Earth might have just been discovered on Mars. And if it's confirmed, it could mean humanity is doomed. This isn't science fiction or fear-mongering. It's a logical conclusion that flows from one of the most important questions in all of science. Where is everybody? We're talking about the Great Filter, a cosmic gauntlet that might explain why we don't see advanced civilizations filling the galaxy. Every time we find evidence that life is common in the universe, we push that filter closer to our future, making it more likely that something catastrophic lies ahead of us. Today, we're going to explore the recent discovery on Mars, why it's different from every other false alarm we've had before, and, most importantly, why confirming life on our planetary neighbor might be the worst news humanity has ever received. The logic is inescapable, and by the end, you'll understand why some scientists are genuinely worried about what we might find. Let's start by imagining two completely different versions of reality, both of which are consistent with everything we know right now. In the first universe, 3.5 billion years ago, two warm and watery planets orbit a young star. On both of their surfaces, chemical soups bubble and complexify and organize themselves into tiny structures that learn to harvest energy, to duplicate themselves, to evolve. Their methods are endlessly creative. On the smaller world, one life form learns to pluck a spark of energy by reducing one iron compound into a slightly more stable one. They take hold in a mineral-rich spot and spread outwards, a metabolic shock wave carving rings into a damp river delta. Who knows what else these clever little organisms might have become given time? How much more complex they might have evolved? But they didn't have time. Their world was small. Its molten core cooled quickly, hardened, stopped spinning. Its magnetic field switched off, and the delicate new biosphere was laid bare to the abrasive solar wind. With the atmosphere lost, the world froze. Its larger neighbor fared better for a while. It held its heat, and so also its magnetism, and its atmosphere, and its water, and its carbon cycle. Life thrived, continued to complexify, and eventually spawned some even cleverer creatures whose metabolic shockwave was much, much larger. They learned to travel between the worlds, or at least to send their robots. And so, 3.5 billion years after some rings were carved in a river delta, the artifacts of two interplanetary neighbors met. The robot of one touched the fossil of the other. In that moment, the remaining life form understood two things: that even now it was far from alone in this universe, and that its doom was closer than it imagined. In case you didn't guess, the small world is Mars, and the large one is Earth. The robot is the Perseverance rover, and the spots are the subject of a recent NASA announcement as a possible biosignature. But now let me give you an alternate version of this story that's at least equally likely. Life only could have formed on the larger world. Abiogenesis, the formation of life from non-life, requires such specific circumstances that it will never happen twice in one solar system, and may happen very rarely in an entire galaxy. The robots still explore, but every pattern found in the rocks, every odd atmospheric composition, turns out to be explainable by non-living processes. They're phantoms of our fear of the truth that we're relatively alone in the universe. We don't know which of these stories is true. Did Perseverance just discover ancient life on our literal neighbor, meaning that life is extremely abundant in the universe? Or will we never discover life because it's insanely rare? It's a hell of a thing to not know which of these wildly different scenarios describes our reality. That's why the recent discovery by NASA is so exciting. We're on the precipice of possibly knowing one way or the other.
Let's look at the actual science before we peer deeper into the existential abyss of what this means either way. The Perseverance rover landed in the Jezero crater on February 18, 2021. The ancient impact site was chosen specifically to optimize the chance of finding evidence of past life. A critical factor is evidence of past water, and it's pretty clear that Jezero was once a lake, with dry riverbeds both entering and exiting the crater.
After meandering the crater basin, Perseverance found its way to the Neretva Vallis region, part of the ancient river delta that fed the lake billions of years ago. Its sights were set on the Bright Angel, an unusually light-colored outcrop in the region, apparently surfaced with iron-rich sedimentary rock that washed in from surrounding regions in the distant past.
And that's where Perseverance stumbled on something remarkable: a collection of millimeter-scale spots and rings that have been dubbed poppy seeds and leopard spots. The patterns sparked immediate interest because they look for all the world just like deposits made by Earth microbes, metabolic rings that expand as a colony grows outward from a central point.
So Perseverance began its detailed work. It drilled samples for analysis, used Raman spectroscopy, and bombarded the ground to analyze reflectance and X-ray fluorescence. Then it sent the data home via orbiting relay, and the team on Earth painstakingly analyzed the transmitted information for many months. The team concluded that the rings and spots are some sort of iron phosphate, while the pale interiors of the rings were an iron sulfide, most likely vivianite surrounding gragite.
The team also found a strong association of organic molecules with these patterns. Now, organic does not mean life, but rather the carbon-based molecules that life tends to use. This all suggested a particular story: oxidation of organic molecules leading to reduction of iron in the sediment into iron phosphates first, and then into sulfides. And this is wild, because it's exactly what certain Earth microbes do. They extract energy via redox reactions of minerals, grow and spread in the process, often leading to similar ring structures.
Alternative explanations do exist. The same reactions can happen in high heat or acidic environments. However, this once warm, wet river delta shows no signs of either. Nor are there signs of potential geothermal sulfur sources that would be the other explanation for the gragite formation. This all sounds pretty exciting, but it also sounds familiar. We've seen these headlines before. Scientists find biomarkers for life, only to find abiotic, non-living processes that can cause the same thing, or at best for the potential biomarker to hang as a mere potential without new evidence to confirm or refute it.
Let's take a look at some of the previous maybe aliens discoveries to see if there's a difference with this one. A little over a year ago, NASA reported the tentative detection by the James Webb Space Telescope of dimethyl sulfide in the atmosphere of a planet orbiting a red dwarf 124 light-years away. This molecule is a major byproduct of microbial metabolism on Earth. There's no known abiotic mechanism to produce it, at least not in the very high quantities needed to explain the observation. However, further observations have not made that detection any more confident. It remains very tentative despite further effort.
In a similar vein, in 2020, a team of astronomers reported the detection of phosphine in the atmosphere of Venus. Again, phosphine is a common microbial byproduct, and so the team claimed this as a potential biosignature. The Venusian surface is pretty uninhabitable, so the idea here is floating colonies at altitudes with conditions closer to Earth. There are also these shifting dark patterns in the Venusian atmosphere, which Carl Sagan proposed could be microorganisms back in 1963, and which seem to show unusual ultraviolet absorption characteristics in a 2019 study. The problem is that neither the phosphine detection has been confirmed, and there are potential abiotic mechanisms for both the phosphine and for the dark streaks. There are plenty more would-be biosignatures, but let's go back to Mars.
or at least to a chunk of it that ended up as a meteorite on Earth after, presumably, being ejected from its home planet by another impact. Scientists found a peculiarly cylindrical mineral formation in this meteorite that they claimed might be a fossil microbe. Chemical analysis is tricky in this case because of earthly contamination, so the speculation is all around the shape of the thing. But then, being the killjoys they're paid to be, other scientists pointed out abiotic means of getting the same structures.
So the common thread here is that previous potential biosignature discoveries either have clear abiotic explanations or have not yet been verified as definite discoveries, or both. The case of the Bright Angel find feels different. There really isn't yet an obvious abiotic alternative, at least not yet. Some new geochemistry could certainly be at work, or maybe some freak circumstances veiled the hot, acidic, or sulfurous history of this region, confusing our interpretation. But previous biosignature candidates have all been quite a bit more tentative or more abiotically explainable.
At this point, it's not possible to assess the likelihood of this being real. The only thing that's possible right now is a kind of gut check. On one hand, almost every potential discovery that promises to revolutionize our entire understanding of the universe turns out to be wrong. These sorts of false positives are expected. At this advanced stage in the development of science, truly revolutionary discoveries are very, very rare, and false positives only have to be slightly less rare to show up more often than the real thing.
Currently, we know of one place in the universe where life appeared, Earth. And we know that life appeared quickly on Earth, which makes it tempting to think that life emerges easily given the right conditions. Even if right conditions means only very Earth-like planets, there are many billions of such planets in our galaxy alone. This implies that life is very common in the universe, or not.
There are strong arguments for why the early emergence of Earth life tells us very little about the broader abundance of life. They come down to selection bias and anthropic reasoning. It's not surprising that we observe our home planet as having life because the alternative is impossible. We wouldn't be here to observe a lifeless planet. But that only puts us on a planet with life, not on one where life formed early, which again, we wouldn't expect if life is improbable.
But there's another factor to consider. The formation of life might be extremely sensitive to the conditions of the planet. In some places, it's pretty improbable. In others, much more probable. The latter may be quite rare, like Earth potentially is. Depending on how this biogenesis probability depends on conditions, it might be that only near-perfectly tuned planets get life, and they get it early because conditions are so favorable. This is the argument made, for example, by David Spiegel and Ed Turner. They show that the early emergence of life on Earth does not guarantee abundant extraterrestrial life. And that's the case if the prior probability of abiogenesis is very sensitive to initial conditions. David Kipping adds to this analysis the fact that significant time is needed for life to spawn a sentient species, and that this time span starts to bump against the maximum habitability of Earth-like planets. He finds that the early emergence of life on Earth is perfectly consistent with life being rare.
But all of this changes if we find one more instance of life in the universe, and it changes massively if we find it on Mars. That's a huge hit to the hypothesis that the initial formation of life is improbable, and to the idea that its probability is super sensitive to conditions. If life formed on Mars, then life is not overly picky about where it forms. And if it did so quickly on Mars, then that short timescale is not biased by the need for lots of time to then form us, as was the case for Earth. The Spiegel and Turner paper also quantifies this in light of the discovery of early life on Mars. In short, the discovery of ancient life on Mars short-circuits the anthropic arguments for life being very rare.
That said, intelligent and technological life may still be very rare, and our non-observation of advanced species arising before us on the galactic scale is evidence of that rarity. This leads to an awkward and deeply troubling conclusion. If primitive life is extremely common, and if it almost never reaches a stage capable of being seen across the stars, then something impedes that development after the abiogenesis stage.
This idea is often framed as the Great Filter, one or more steps in the development of civilizations that are so ridiculously hard to cross that very few potential starting points actually make it all the way to star-hopping, science fiction mega-civilization status. And the question has always been, is humanity one of the lucky few that has passed its Great Filter? Or is that filter still ahead of us?
Was that hard transition abiogenesis itself? Or the development of complex cells? Or big brains? Or all of these together? Or is it the survival from digital age to space age that's so damn tricky, due perhaps to species almost invariably wiping themselves out through nuclear war, artificial intelligence gone wrong, engineered pandemics, or environmental collapse? We don't know, but the more we rule out great filters in the past, the more likely it is that the great filter is in our future. Nick Bostrom and others have articulated this argument with chilling clarity. Currently, the probability of abiogenesis on a given suitable planet could be as small as 1 in many, many billions, because anthropic selection allows such a rare phenomenon to be observed by the observers it produces, even if that's one life form per galaxy or per universe. Or the probability of abiogenesis could be closer to 100%, which means many billions of instances of abiogenesis in this galaxy alone. But the filter has to be there somewhere. We don't see aliens. If we eliminate early filters, then later filters have to pick up the slack.
Abiogenesis could do a lot of work in pushing the filter into our past, making us feel safer. But an observation of life on Mars reduces the filtering effort of abiogenesis by a factor of up to many billions. If we have found life on Mars, at the very least, we should stop taking for granted that we'll survive into the future, because there's now even stronger evidence of our existential risk.
I should add that there's another story that allows us to keep feeling special, and that's panspermia. It could also be that life formed only once and early on either Earth or Mars, and then early microbes hitched rides on impact ejecta to travel between the planets. Then we're back to wondering if we're alone, and we also get to wonder if we're Martians, which would be a fascinating twist to the story.
But putting existential anguish and planetary identity issues aside, let's allow ourselves to be excited at the potential discovery of our extinct planetary neighbors, at least for a bit. Did we find life on Mars? We can absolutely know for sure whether the bright angel patterns were biological when we can collect those samples. Perseverance packaged the samples and left them waiting for an upcoming mission designed to return them to Earth. That mission was canceled in the last White House budget, so there's that. There was some verbal backtracking after the NASA announcement, but the retrieval of those samples is pretty unclear at this point.
It seems to me that in these times of division, our first discovery of life on another world could be just what we need to reignite some collective pride in our species and our achievements. And maybe, just maybe, it could help us get on with our real job of cooperatively exploring and perhaps even contacting a life-filled universe, assuming we can navigate whatever great filter still lies ahead of us.